Okay, sorry. So I'll just continue the class. So I'll begin with the weak maximum principle. Okay. So basically, okay. So what does the weak maximum principle say? Let omega, subset of R2. First we'll talk about R2, then we'll extend our principle to n dimensions. Be a bounded domain. Bounded domain, and let U belongs to C2 of omega intersection C of omega bar be a harmonic function then maximum value of U is achieved on boundary. So any function that basically satisfies del u equals to 0, you solve this particular partial differential equation, but without solving you can tell one property is that it will attain its maximum on the boundary. Yeah. What's happening? So I've given the detailed proof, but I'm just skipping the proof. So just a proposition. If U belongs to C of omega bar satisfies the mean value property in omega, then it cannot attain maximum or minimum in interior of omega. Okay, from a mean value property, so now arises a question that now you solve the Laplace equation. Does that imply that can you get two different solutions for the PD? Like, right? So I'll state the theorem, uniqueness of Dirichlet boundary value problem, Dirichlet boundary BVP boundary value problem, where it basically says is that let omega be a bounded domain on R1 and F belongs to C of omega and G belongs to continuous functions that are differentiable on the boundary of omega, then there exists only at most one solution to the BVP, to the boundary value problem minus delta U is equals to F with boundary condition G. See, the simple reason for that is the mean value, the maximum value principle. You just subtract, say, two solutions satisfies this, and just you subtract them. So minus delta of u1 minus u2 should be 0, and u1 minus u2 on the boundary should be 0. This implies that because the maximum value is attained on boundary, so 0 is the value of the solution. Implies u1 equals u2. So after solving this particular PDE, you get one solution. Okay. Okay. So let's go to the next topic. So I'll just state some, these are some theorems that an engineer won't understand that easily, but because there are some mathematicians in my class, to cater to them, I'm just teaching this inequality, Harnack's inequality. Suppose U is harmonic in omega, then for any subset, any proper subset omega bar of omega, there exists a constant such that superior of on omega bar is less than or equals to c times infimum of E bar. This property is satisfied in higher dimensions, but I'll write a simplified version of this particular inequality in 2 dimensions. Okay. So in a 2-dimensional case, sure, 2-dimensional case. So I'm just stating the Harnack's inequality. If f is non-negative function defined on a closed ball in Rm with radius R and center x naught. If F is continuous on the closed ball and is harmonic on the interior, in its interior, then for every point x, this equality satisfied. So basically r minus r by r plus r times f of x naught is less than or equals to f of x naught less than or equals to r plus r by r minus r f of x naught. So this is Harnack's inequality. I have written down the inequality properly in the notes. If you have doubts, always you can WhatsApp me anyway. Okay, now let's go to the next theorem. Yeah, so I'll just define something. So just a definition of harmonic and subharmonic functions. Let U belongs to C2 of omega. We say that U is subharmonic on omega, obviously, if minus delta U is less than or equals to 0 and U is superharmonic if minus delta U is less than or equals to 0 in omega. So theorem. So if U belongs to C2 of omega and is subharmonic, then for any unit ball around epsilon, U of epsilon is 1 by omega n minus 1 r n minus 1 integral dou b epsilon r. So U of x and so on. So for subharmonic functions, the mean value is lesser than the average taken out by integral. There are things of kind of, I mean, so far the discussion on PDEs is like abstract. Now let us go further to the fundamental solution. Of Laplacian operator or the Laplace equation. So far, I mean, I have given it as an exercise to show that Laplace equation is invariant. So basically, B epsilon of x can be written as phi double dash of x. I mean, this is basically the Laplace equation in the polar coordinates, something that you have to solve. I mean, we are solving the Laplace equation. I mean, we are converting it to the polar form, and now we are solving it. Once you solve this and I mean in the polar form, now you just solve it. It's simple OD. Once you solve it, you get psi of r as c times log mod r by c, c by 2 minus n, or 2 minus n is 2, and greater than or equals to 3. So basically, it's not defined at r equals to 0. So this particular equation is valid only if del psi is 0 if on Rn minus 0. So you are this is called something called the fundamental solution, and note that your fundamental solution does not satisfy the Laplace equation for this to be fun. We'll just ponder upon this particular idea for a while. The next lecture, this and next lecture will be on the fundamental solution of Laplacians.